Alright, so what we will do now is we will show you a simple demonstration of what a mechanic would want to check if a car or a vehicle comes for maintenance, okay, or if he wants to do a regular preventive maintenance check of all the parameter IDs specific to the vehicle. Please note that I mentioned to you some time back that the number of ECUs in a vehicle can exceed even 70 to 90, anywhere between 70 and 90 ECUs. While that is what will happen in reality, as far as this lab demonstration is concerned, let us put our attention on the engine ECU. Okay. So, you can see there is an engine ECU here. We will show you, I will show you some of the parts of this engine ECU. You have already seen this 5 knobs, and these 5 knobs essentially correspond to coolant temperature. This is engine RPM, and this is vehicle speed, and this is oxygen, and this is mass airflow. Okay. So, you can have anomalies of different types happening within the engine. So, just let us concentrate only on the engine ECU. Now, back to this picture here, you will see that if you keep the system like this, I will hold it like this perhaps. If you hold the system like this, you will see that OBD2 is written here, right. This is the OBD2. This is a OBD2 connector, and this OBD2 connector essentially has what is inside this little box here will have another controller called ELM327. Okay. This ELM327 essentially has the ability to connect on one side to OBD2 connector based protocol, which essentially uses CAN protocol, and if it is using CAN, it has to use ISO 15765-4, which essentially is the CAN protocol. All that is protocol based data is available on this OBD2, and ultimately if it has to be useful to a mechanic, the mechanic can connect a handheld device and pass commands directly, okay, that is one way. But if you look at an IoT device, you could essentially use a mobile phone to do the same, and therefore this device has the ability to take OBD2 commands on one side and convert them into equivalent Bluetooth low energy packets, which means that it now becomes amenable for viewing on several Google Play apps that are available. You can see these values. Okay. One such app is downloaded, you can pick any app that gives you. I mentioned to you about Campana as one such app. We can also show you that this app called Torque, TORQUE. So, you could download any of these apps and look up the engine ECU parameters. Now, you can see that there is an LED blinking here, and this LED blink simply indicates that everything is connected, and particularly the BLE is connected, that means the mobile phone is connected. This phone along with this OBD2 setup is one possible setup that you can imagine. Now, imagine that this part, this particular ECU is the engine ECU, it is part of the car or a vehicle, and all that the mechanic has to do is locate the OBD2 port and push this connector inside, and then use his mobile phone to see the different parameters. So, now what I will do is I will ask Vinod Hegde to move these knobs, and then I will perhaps hold this phone for you to see what is the impact of these connectors. Alright, so maybe he should come and then turn the knobs one by one. What are you turning now? He is turning mass airflow. Can you now see it does increase now? Okay. So, that is a nice thing there. The second one is oxygen. So, you can see oxygen is also increasing. Please note, oxygen is an output sensor, right. Mass airflow is an input sensor. Essentially the mass airflow is connected between the throttle body, there is a throttle body, there is an air filter, and essentially this throttle body input basically takes the mass airflow which is measured. So, mass airflow essentially is grams per second is a unit, and essentially it is an input to the whole system of combustion. Oxygen is what you are measuring as an output, and that is expected to be as low as possible, only then you realize that the combustion has happened successfully, right. So, let us go back and see how the oxygen sensor manipulates. Okay, so let us change the oxygen sensor value. Okay, there you are, there are some typical numbers which can happen. Essentially if you look back, the mechanic can do things like the following. He can connect this device, to the car or vehicle and then drive it for about, let us say, a kilometer or two, and then look up these values as and when things happen and see it spots some anomaly by looking. But this is not the best way to do. You need a complex event processor which essentially storing these values on board and perhaps taking some real time decisions and showing you some real time thresholds as and when the driver is actually moving along the vehicle, right, when he is actually driving the vehicle. This is what I am showing you right now is for a mechanic to spot the anomalies by connecting a device. This is not the way you want to do. You want to be alerted as and when you are driving at high speed or whatever on a highway. If there is an anomaly, it should show up. I also mentioned to you that the front panel of most of the cars that you see today, you will have a MIL indicator, it is called the malfunction indicator lamp, and that is the only indicator that sort of tells you something about the fact that the engine throttle body there is some issue there. So that is the only light that will essentially go up. Okay, battery is shown separately, the oil indication is shown separately, there is a temperature dial which is also there measuring the temperature of the engine and corresponding systems connected also to the coolant temperature. So therefore this is what would be very useful for you to sort of connect. So one can now see that it is highly limited, this is something only that the mechanic can do. Let us shift focus to see if we can essentially automate all this inside a vehicle and then see if there are automatic indications that can be generated. Let us move to the following scenario of automatic alerts that have to be generated or automatic action that has to be taken in real time inside a vehicle, right. You have to take some action. What we did previously was only for a mechanic to identify some bugs in the system. By the way, just to mention to you that the previous app that we showed you in terms of the different numbers that were flashing on the screen of an Android phone, the application is called Torque, TORQUE. You can download and you can try. Okay, like Campana, it is also another app. So just giving you several options that you do not have to stick to any given app. Now imagine you are inside a car. Okay, you are inside a car and you are driving at some good speed, and this ECU is here. The ECU as usual is monitoring several parameters for you. You can see that this CAN interface here in this demo, the CAN interface does not have a Bluetooth OBD2 output ELM 327 based system, but indeed it is going in this direction and then going and connecting to this little piece of hardware. So let us see if the camera can zoom to, yes, you see it is connecting to this piece of hardware. Now what this piece of hardware does is, you can get this easily from SparkFun. This is a CAN bus shield. Okay, this is a CAN bus shield. That means this CAN connector is essentially connected to that. Very good. This board, the one down below here, is, you see this cable here, this is connected to an onboard computer in the automobile. Okay, this is the setup. and then in this setup it has to detect anomalies in real time, has to ensure that it alerts you. Recall what we discussed about mass airflow, right, and anomalies with respect to throttle body, the butterfly valve and so on, right, or engine coolant temperature, for instance. Rise in coolant temperature is a big anomaly. It has to, the vehicle perhaps has to halt almost immediately to take corrective action. So somehow you have to do that actuation, right. So those issues have to be highlighted. Therefore how will you do these things? Now the question is, how can, if you imagine yourself to be a programmer, imagine yourself to be as an automotive engineer, you have to put the system on board of a vehicle. For that, what you would do is you would use a stream processing platform, and such a stream processing platform is WSO2. Okay. This is one such platform. There are many open source platforms. There is one more called TickStack, that is also an open source platform. So you can use any open source platform you are very comfortable with. And to understand what exactly is the WSO2, because we will do a demonstration with WSO2, let us turn to the computer which essentially shows a display of what WSO2 is. Here you can see that WSO2 is a stream processor, is an open source, and it is light weighted. It is a streaming SQL based platform, okay, and enables you to do running aggregations to detect patterns and generate alerts on data streams in real time. Beautifully connects to the kind of anomalies that we are looking at. This picture says it all. Left side are several app services and sensors which are there, like MAF sensor, oxygen sensor, then coolant temperature sensor. All these sensors are there which does some sort of pre-processing, and the ECU has all this data. This data which the ECU has will have to be somehow pushed on to the dashboard for some sort of display. The onboard computer has to take the data and then has to make it available to an onboard computer based system. So essentially all the different sensors which are giving away data will have to be collected by the ECU. One can think of protocols like MQTT, COAP and so on. Here you can see that this WSO2 supports MQTT as a possible IoT protocol. All that collection happens and then now comes to an onboard computer. The onboard computer is the place where actually the WSO2 is running, and that is where all the analysis is happening. You can see it does analyze transformations, complex event processing, okay, all the machine learning model serving, then streaming machine learning, anomaly detection and so on and so forth. All that data that is coming from these sensors, some of them that are useful are kept, some of them are not so useful, which are well within standard limits are thrown away, and the analysis is happening in real time as and when the data is coming from these sensors. So the left side is feeding to the middle one, analyze. Now if you see an anomaly, you should act upon it, okay. So the act could be in terms of an alert, it could be in terms of something appearing on the head on display of an automobile, or it could be in terms of action, halting the vehicle, or in terms of making a standardized interface for other actuators to work with, which is essentially the APIs that you can see there. I suppose if you have third party actuators, you need to release an API which essentially will feed to that API, and some third party would essentially pick that system and then do its own actuation, perhaps it has its own generic actuation. So that part would be also something that is possible. So now what we will do is we will have to show you what the OBC is actually collecting all the data, right. Remember there is the collect data, analyze data and act upon the data. So the collection part is coming from several sensors. In this case we have limited to just the engine ECU related sensors. So turning our attention to the screen, the first one that you see is temperature, and then you have oxygen, you have mass airflow, you have speed and you have RPM. All of them are set to some typical numbers, and then you will have to now you are essentially defining those typical numbers, and then you will now catch anomalies based on those typical numbers that have been set up here. Alright, so this OBC is continuously getting this data. Alright, now let us turn our attention to what is actually happening. You can see that this part of the code essentially is collecting data from all these sensors using a protocol as I mentioned like MQTT, and let us just concentrate on coolant at the moment. Okay. You can see that the paper was saying 90 degrees to 105 degrees is considered to be normal, anything greater than 105 degrees is bad, is dangerous, and less than 90 is also not the right thing to happen. So if you are really looking at an MQTT system, and OBC is collecting data and processing data and all that, if you are repeatedly getting 90 to 105, what would you do? Just to save space, you would look at the data and discard the data, right. So you can have one MQTT publish which says normal, okay, something called normal. I will show you the exact part when we go, because Tejaswini has already set it up. Like that you can say MQTT publish, you can also say high, right, you can also say high, you can also say MQTT publish low, okay. We will show you one by one perhaps for you to get a feel. So what should happen? If you see these three things, and if I turn the knob of coolant temperature, the dashboard should indicate that there is a problem with the coolant temperature, because it is now it has intelligence inside. The complex event processor has been assigned certain thresholds, and it is just looking at these thresholds and alerting once the value cross a limit. And for this particular display purpose, since we do not have a automobile here or a dashboard, what we will do is we will switch to a normal mobile phone, and maybe we can show you some numbers on that mobile phone. Let us see if we can pull off this demo. Alright. So now is to look at the code and look at where is normal, where is high, and where is low as far as MQTT publish is concerned. So let us look at that part of the code. So you see pub lower, is that lower? Stream temperature lower, okay. It has been defined as less than 90. Can you go to and flash on that? Exactly. You see temperature less than 90 is shown there. Alright, now let us go to publish normal. What is normal? Normal is two thresholds, right. It should be between 90 and 105, that is what she has coded, and you can see that that is normal. Then you have publish higher, so that is also coded. So you have these three thresholds. Great. Now the system is set up for checking whether coolant, if it goes high, what is it that is going to happen. So now let us see what is its current status of coolant temperature. It is at a very low value, some minus 40, and now what we will do is we will turn the knob, and we will ask our camera to catch that anomaly. Yeah, let us see if Vinod Hegde is turning it, and now he changed the knob. So he is changing the coolant temperature, he is modifying it, and moment it catches a value, let us now turn our attention to the screen back. So let us see if she can highlight Tejaswini on the fact that the knob has indicated a higher value. You can see it is 114 now, which is a clear indicator that the value has gone up. Now it is okay to see it on the OBC, but the driver should get it, right, which means that part of the screen should also show here. So let us see if our camera can catch this screen as close as possible. There you are, 104, yes, very good, it shows up, thank you. So it shows up 114. This is what the dashboard of the driver will indicate, okay. So one can go on like this and essentially look at different anomalies, what could be happening in the using this kind of a framework. The second anomaly that we may want to show is perhaps with respect to MAF, right. So let us see what the code of MAF is, and let us see what is the current value of MAF. By the way, this code will be available to you on the usual website. So if you wish to open it and then have a look at it, should never be a problem. So let us look at MAF code. So the MAF code is shown here. MAF value is another sensor again published by MQTT. This sensor is taking it, and you can see MAF is shown. Where is the MAF here? Yes, MAF query. Yeah, you can see that is the MAF query there. You can go on like this and you can look at several anomalies. One other anomaly that you can look at is the mass airflow. The system in this board, the ECU system that is available to you, oxygen is measured in voltage levels, it is between 0 and 1 volt. If you look at other sensors pertaining to the engine ECU, oxygen sensor I have mentioned to you is an output sensor. You should see a very small value of oxygen, which is corresponding to the fact that all the air that has come in, there is a good mixture of air and fuel. The right time the ignition has happened. So the fuel injection system is working efficiently well. Typically it is not going to be 0, so it is going to have some value. From what we know that these values typically range from 0 to 1. 1 means high, extremely high. 0 means there is no oxygen at all, a very ideal situation. So you typically look for a normal range which is around 0.45 or so. So let us see, yeah, it is about 0.45 you would say. So it should be as low as possible, but okay. So 0.45 volts if you are able to measure on our ECU system, we would regard it as something which is okay, which is not a malfunctioning. Similarly MAF is typically between anywhere up to a maximum value of 655. You can't have 0 MAF because some oxygen has to go in. So you would typically say it should be higher, as close to something as much as 655. Again in this ECU this range is around 345, it would go till there. And now what is the anomaly that you want to create? The anomaly is that if MAF is greater than 250, is not really an anomaly, but you want to do it along with oxygen sensor. So you are not observing single value, single parameter, but you are looking at multiple parameters in one go, alright. This can be regarded as an exercise that you have to look up, read literature and understand what is a good number. So I will put the question here, what is a good number? What is a good number for MAF and O2 to be regarded as an anomaly, right? This is the question. We are not going to answer this, you will have to figure out, read literature. So we are looking at two sensors together. The point I am trying to make is, if you look at the setup which we have put together from our lab, the WSO2 platform has also the ability to do stream processing on multiple parameters. Very complex set of parameters can be tuned and you can catch anomalies with respect to those multiple parameters. This is indeed the power of complex event processing, which is essentially doing stream processing. Multiple thresholding is something that you can do. Therefore it is a very powerful engine which is running, not just about analyzing, but it can also do storage of these anomalous events, which can then be uploaded to a cloud for slow loop analysis. So the combination of real timeness and slow loop analysis by uploading data is an interesting part of this stream processing application. Alright, so now let us look at these two MAF as well as oxygen sensors. You can see that Vinod Hegde is trying to play with the MAF sensor, and also he is trying to tune the oxygen sensor to create an anomalous event. And now let us go back and look at the screen here. If he does that change, the screen here is essentially indicating a value which is greater than 250, which is indicated as a sort of an anomaly, and oxygen at the moment is 0, and which means it is okay. But if he changes back here, let us see if he does this change the value from oxygen to a different value. and then it should indicate 1, right. So, let us see if it is indicating 1. Okay. So, let us see here, yes, you can see that there is a subscription to high oxygen and MAF, that means these are 2 ECU parameters, and oxygen is indeed high. So, let us see if it can indicate those anomalies. So, you can see that it is indeed indicating 1, which means it is a anomaly, right. So, you can see oxygen voltage is higher and then it has created an event. One more anomaly that you may want to catch with respect to rash driving, right, you want to catch rash driving. Well, you should be able to get this from the speed, right. Essentially speed should be an indication, and therefore if the speed is going beyond a certain threshold, you may want to say that driver is under a rash condition and indicate that rash condition immediately. I am sure you have all experienced sometimes when you hire a cab or something or some other public transport service and you find that the driver is rash, you may want to report. That is one way. The other way is the values that are coming from ECU itself can log it and store it and also upload it to cloud, or it can immediately indicate to the driver that the driver is actually driving this vehicle very rash. Okay. So, the question, second question is how to catch rash driving from the code available to you. So, you will have to write simple algorithm to indicate the rash driving. If you wish, you can look up that paper that we discussed. That paper has some hints there, so you can use that. Thank you very much.